So my name is Sofia Kirsanova. I'm a PhD student at the University of Minnesota, and I'm a member of Knowledge Computing Lab. So today I'll be sharing work I've been doing as a part of the DARPA critical mass project focused on automating the detection of legend items on scanned historical geological maps. Next slide, please. So today I'll start with the motivation for detecting map legends and its role in automated map interpretation. Then I'll outline my research goals and key challenges, especially with our historical and geographical maps. I'll explain how we're using GPT-4 with the in-context learning, describe the prompting strategy, share some experimental designs and results, and I've also introduced a new direction. It's about extracting chronological relationships between legends, and conclude with how this work supports the broader map analysis and geospatial applications. Next slide, please. So historical geological maps, they're full of available information like landforms, rock types, mineral zones, and more. But this information is encoded visually through symbols, textures, and color patterns. So the key to interpreting those symbols lies in the legend, which acts as, I would say, decoding guide. And if you want to analyze maps at scale across thousands of sheets, we can't rely on manual legend reading. It's because it's tedious and slow. So automating legend detection would make it possible to unlock structured map data and integrate it into geospatial databases and pipelines, and including things like mineral explorations and historical landscape change analysis, for example. And beyond this specific task, legend detection is a critical piece of the larger critical mass project funded by DARPA and USGS. And the broader goal is to use AI to analyze historical maps to help locate critical minerals. So resources like lithium, cobalt, and because they're essential for renewable energy and national security. Next slide, please. So on this slide, I want to show you why detecting legend items is so important. On the left, we see a historical geological map without a legend visible. And it's full of textures, colors, lines, but without any context. And we don't know what any of it means. So is there orange, like maybe it's a sandstone, or is that dark patch like coal or volcanic rock? But can you please, like, I have an animation there, next slide, please. Oh, yeah, thank you. So on the right, we have added the legend, and suddenly the map becomes readable. Each color and pattern corresponds to a geological unit, age, or formation. And this comparison shows the key idea. Without legend, the map is just symbols and colors, and with legend, it becomes structured knowledge. And that is what we're trying to extract automatically. Next slide, please. The main goal of this work is automatically detect and localize legend items and their corresponding descriptions on scanned historical geological maps. While that sounds pretty straightforward, there are several challenges that makes it difficult. So first, there's lack of labeled data sets, and annotating these legends, especially at high resolution and with precise item description pairs, is time-consuming and requires a lot of visual judgment. There is also class imbalance because some symbols and descriptions appear frequently while others are rare. And it makes it really hard to for any model to generalize well across all legends content. We also deal with uniform spacing. It means that items and their descriptions may be unevenly placed or separated across lines. So, and it breaks the assumptions about the alignment. Related to that, there's spatial proximity doesn't always equal semantic pairing. Just because two elements are near to each other, it doesn't mean that they belong together. And this leads to false matches. Finally, the layouts are also very inconsistent. Some legends are stuck vertically, others are arranged horizontally, and the position of the item relative to the text varies a lot. So all these factors make this like a complex visual understanding task, and not something like easy solved by template matching or simple heuristics. Next slide, please. So here is an overview of the full pipeline we're using to detect legend items and their descriptions. So firstly, we start with the full historical geological map. It's the input of the whole pipeline. Use the model layout and V3 to detect and prop the legend area from the rest of the map. And this lets us isolate the part we care about. Next step is to use GPT-4 within context learning. This means that we give the model a few labeled examples as part of the prompts, like shown here on the top. And then ask it to return bounding boxes for legend item and its descriptions to the new image, in the new image. The model's output gives us normalized coordinates, which brings us to step 3, and we scale those values back to match the original size to the cropped image. The result is a set of bounding boxes, so one for each symbol and one for each description. We can now use this downstream for downstream map understanding or conversion into structured data. Next slide, please. Yeah. So there are a few questions that usually come up at this point, so I want to address them briefly. So firstly, we crop the legend area firstly to reduce the noise and keep the task focused, because the full map contains a lot of unrelated content to this task, especially like terrain, geographical patterns, labels, and anything else, which makes it much harder for the model to focus on just legend area. By isolating the legend area first, we simplify the problem and get more accurate bounding box prediction. Next, the GPT-4, still this slide, thank you. GPT-4 normalized coordinates. I'm sorry, previous slide. Yep, thank you. So as I said, GPT-4 normalized coordinates mean that values are between the 0 and 1 relative to cropped image size, and to convert these pixel coordinates, we multiply the normalized values by width and height of cropped image. This lets us draw the bounding boxes exactly where the model thinks the legend items and descriptions are. And like what actually prompts like, I would show you exactly how it looks like on some next slides, where I break down the prompt format and why we choose it. Well, now next slide, please. So this is the typical prompt. This is how it looks when we are using GPT-4 to predict legend item and the description locations. So each example includes a pair of bounding boxes and one for legend item, and which is usually a colored box or symbol, and one for description, their associated text block. We format these coordinate parts representing the top left and bottom right corners of the box, and these values are based on cropped image of the legend area. In the prompt, we show the model 15 of these item description pairs, and then at the end, it's give an empty slot with question marks, where the GPT-4 is asked to predict the next set of coordinates based on the pattern it learned from the previous examples. So using this format, the model outputs very structured results, and the JSON style format helps to reduce ambiguity, the formatting drift, and like everything bad in the responses. Next slide, please. So I ran a series of experiments to understand how different design choices impact the performance of legend detection and description pairing. So first, we compared several models like layout on V3, for the whole task, segment anything in combination of the extract GPT-4 and GPT-4 with context. GPT-4 with context outperforms their others in both legend item and description detection. Next slide, please. So second, I tested how many examples to include in the prompt. We found that 15 examples worked best. More than that led to overfitting, where models began to rely on the prompt structure. Next slide, please. So fourth, we looked at the legend shape. Third, so thirdly, we looked at the legend shape. Not surprisingly, but rectangle legend items were much easier for the model to detect than custom or regular shapes. And finally, I tested prompt formats, natural language. Next slide, please. Natural language, plain text, JSON style. JSON constantly gave the best results, and it was easier for GPT to parse and reproduce accurately. And these experiments helped refine both the model setup and the prompt design, and gave insight into where the model struggles the most. Next slide, please. So summarizing the experiments, we found that GPT-4 with in-context learning provided the most accurate detection of legend items and descriptions. So yeah, legend item shape played a role. JSON style prompts worked better than natural language and plain text. So now I would like to concentrate on like some of the next steps. Next slide, please. So our next step in this research is to move beyond the simple item description pairs and start working with chronological information found in correlation charts. These charts often appear in geological maps, legends, and show how different formations or units correspond to geological time periods. So this presents a new challenge. How do we detect not just boxes and text, but how do they relate across columns and layers? Next slide, please. Yeah, next slide. So currently we're exploring how to extract and represent this structure and whether GPT-style models can reason about these more abstract spatial relations. So on this slide, I'm showing their examples of chronological information, how chronological information is often represented in map legends. Unlike previous tasks where each legend item had a direct one-to-one mapping with description, it is much more complex. Here we're dealing with multi-level structured relations between legends and time periods. So, for example, on the leftmost picture, you can see that their vertical hierarchy showing broader geological areas on the right, like Mississippian, Cambrian, and some units span multiple periods, and there is a vertical stacking that implies ordering and not just labeling. Next slide, please. So this raises new challenges. So what happens? What map has multiple legends? For example, some describing symbols, others describing chronology. How should we present correlations? And because they aren't just links, but grouped and layered associations. How do we extract and interpret the structure? Because it's not just recognizing text, but understanding how different legends align with geological ages. So this is an open challenge in my project, moving from detection to interpreting structural meaning in legend layouts. Next slide, please. So thanks again for your attention today. I'm Sofia, a PhD student working on AI and historical maps. And this work is a part of critical math project at the University of Minnesota. And I'm always happy to chat about anything related to AI, spatial reasoning, multimodal learning. So feel free to reach out if you're working on something similar or just want to connect. Thank you.